Welcome, my friends! Today we will be discussing the OneWay ANOVA hypothesis test using the TI-84 calculator. If you want to see a more in-depth by-hand procedure using all of the formulas, check out the video in the description. ANOVA stands for Analysis of Variance, and the title refers to the procedure, which involves segmenting the variance of a dataset into two different sources of variation, which we will discuss more when we get to an actual problem. We will be discussing how a OneWay ANOVA test can be applied to determine if there is a difference in the mean of at least one out of three or more populations using the F distribution. The F distribution is a right-skewed distribution that looks something like this. Like the z, t, and chi-square distributions, the F distribution is a continuous probability distribution used in many hypothesis tests. Values of the F distribution are always greater than or equal to 0. The F distribution is right-skewed, as can be seen from the graph. This contrasts the F distribution with the z and t distributions, which are both symmetric. The exact shape of the F distribution depends on two values: the treatment and error degrees of freedom, often called the numerator and denominator degrees of freedom. We will discuss how to find these degrees of freedom later. Let's quickly discuss the assumptions required in order to conduct a hypothesis test using OneWay ANOVA. There must be a quantitative variable gathered from three or more independent groups. Randomization must be used to gather the data for all groups. The population distribution of each group must be approximately normal. The variances of each population must be approximately equal. The null and alternative hypotheses for a OneWay ANOVA are relatively straightforward. The null hypothesis is that all k population means are equal, where k is the number of populations you are comparing. The alternative hypothesis is written out in words, and is that at least one population mean is different from the other population means. Theoretically, you could write out this using mathematical notation, but it becomes very tedious, especially for a large number of groups, so we typically write out the alternative hypothesis in words like this. Now, you might be noticing that the alternative hypothesis really isn't all that informative. There are many different ways that the alternative hypothesis could be true. Mean 1 could be different from all the other means. Or, mean 1 and mean 2 might be equal, but different from the remaining means. Or, perhaps all k means are different from each other. Rejecting the null hypothesis tells us that at least one of the population means is likely different from the others, but we don't know which one or ones differ and in what way unless we conduct further tests. If we want to know what specific means differ from the others, we have to use the two-sample mean test and compare every possible pair-up of the k means. The problem with this procedure is that, since you are conducting so many tests, there are many possibilities to make an error. There are ways to correct for this problem, but we won't be discussing them in this video. We will just be focusing on the OneWay ANOVA procedure. The ANOVA procedure consists of comparing two different types of variance: the variance between groups and the variance within groups. This table shows the time it takes students to complete a quiz in minutes from three different sections of an intro statistics class. The variance between groups is what is called the sum of squares treatment, or SSTR, and relates to the idea that the mean of each group is different. The mean varies between the groups, so Section 1 has some mean quiz completion time, Section 2 has a different mean completion time, and Section 3 has yet another mean completion time. SSTR grows larger when the mean of these groups are very different from each other. The variance within groups is called the sum of squares error, or SSE, and relates to the idea that there is variance within each group, meaning not all observations in each group are the same. SSE grows larger when each group has values very spread out from the mean of that group. For example, if the quiz completion times in Section 1 were all very different from each other, that would increase SSE. Or if the quiz completion times in Section 2 were all very different from each other, that would also increase SSE, etc. The sum of squares total, or SSTO, is equal to SSTR plus SSE, and represents the total variation in the dataset. As with all hypothesis tests, we need to calculate a test statistic and p-value. The test statistic doesn't have a simple formula like it normally does. In the case of ANOVA, we need to complete what is called an ANOVA table to find the test statistic. The last number in the table is an F value, which will be the test statistic used to find the p-value. The formulas for the sum of squares are complicated and time-consuming, so we will be solving for them in the calculator. What you will need to remember is that the sum of squares treatment plus the sum of squares error is equal to the sum of squares total. We also need to know that the degrees of freedom treatment plus the degrees of freedom error is equal to the degrees of freedom total. K is equal to the number of groups that we are comparing, which is used in the degrees of freedom calculation, and N is the total sample size. Sometimes you might be asked to finish a partially completed ANOVA table, like this one here. It's very simple once you know the formulas. The sum of squares treatment and the sum of squares error must add to the sum of squares total of 100. So that means the missing sum of squares is 60 in this example, as 40 plus 60 is equal to 100. You can also get this by taking 100 and subtracting 40. Use the same idea for the degrees of freedom. The degrees of freedom treatment plus the degrees of freedom error is equal to the degrees of freedom total. So the missing degrees of freedom is 4, so that 4 plus 30 is equal to 34. You could also get 4 by taking 34 and subtracting 30. If we recall the other formulas, the mean square treatment is just the sum of squares treatment divided by the degrees of freedom treatment. So we have 40 divided by 4, which is 10. The mean square error is just the sum of squares error divided by the degrees of freedom error. So we have 60 divided by 30, which is 2. The F test statistic is just the mean square treatment divided by the mean square error. So we have 10 divided by 2, which is equal to 5. You might be asked a few questions about the ANOVA table, such as how many groups are being compared? Well, K is the number of groups, and the degrees of freedom treatment is K minus 1. So that means there must be one more group than the degrees of freedom treatment. So 4 plus 1 is equal to 5. 5 groups are being compared. What is the total sample size? Well, N is the sample size, and the degrees of freedom total is the total sample size, N minus 1. So the total sample size must be one more than the degrees of freedom total. So 34 plus 1 is equal to 35. We can also calculate the p-value, which is just the area in the right tail of the F distribution, greater than F equals 5. On the calculator, we go to second, distribution, scroll down to FCDF, the lower bound is 5, and the upper bound is 1000 to represent positive infinity. The degrees of freedom numerator is the degrees of freedom between groups, or 4, and the degrees of freedom denominator is the degrees of freedom within groups, or 30. Paste and press enter, and we have the p-value of 0.0033. Here is the p-value as you would see it on the F distribution. It is the area greater than F equals 5 that we calculated using the FCDF function. Let's take a closer look at our quiz completion example. The following table shows the time to complete a short quiz in minutes from a random sample of students from 3 statistics sections at a particular university. Assume the 3 sections are independent with approximately equal variances and follow approximately normal distributions. Is there enough evidence to suggest that the mean quiz completion time differs for at least one of the sections? Use a 0.05 level of significance. Let's move on to the 3 steps of the hypothesis test. Step 1. The null and alternative hypotheses. The null hypothesis is that all 3 means are equal. The alternative hypothesis is that the population mean quiz completion time of at least one of the sections differs from the others. Step 2 is the test statistic and p-value. This is where we complete the ANOVA table from the output in the calculator. On the TI-84 calculator, press Stat, Edit, and then clear your lists by hovering over them and pressing clear and then the down arrow. Enter in the data for each sample into each list. Now press Stat again, arrow over to tests, and then press the up arrow. Press enter to select ANOVA. Now press second, 1, comma, second, 2, comma, and second, 3 to enter in the 3 lists. If you had more than 3 groups, you would have to add list 4, list 5, etc. Press enter and we get the ANOVA output. If you scroll down, you see even more output. From the output, we can complete the ANOVA table. The F value is 2.5. The P value is 0.1623, which doesn't go into the table. The factor information relates to the treatment or between groups variation. The degrees of freedom treatment are 2, the sum of squares treatment is 30, and the mean square treatment is 15. On the second screen, which is just scrolled down on the ANOVA output, we have the error information, with 6 degrees of freedom, 36 sum of squares error, and 6 mean squared error. We can find the sum of squares total by adding the sum of squares treatment and the sum of squares error. 30 plus 36 equals 66. We can find the degrees of freedom total by taking the degrees of freedom treatment and adding the degrees of freedom error, which is 2 plus 6, which is equal to 8. If we graph the distribution, the p-value is in the right tail of the distribution and corresponds to the area on the F distribution greater than 2.5. We can verify the p-value from the calculator by going to second, distribution, scroll down to get to FCDF, enter the lower bound as the F statistic of 2.5, and the upper bound of 1000 to represent positive infinity. The degrees of freedom numerator is 2 for the treatment degrees of freedom, and the degrees of freedom denominator is 6 for the error degrees of freedom. We get 0.1623, the same p-value that the calculator gave us earlier. This is also the area in the right tail of the distribution. Step 3. Decision and conclusion. We use the same decision rule that we always have for any hypothesis test. If the p-value is less than or equal to the level of significance alpha, then we reject the null hypothesis. And if the p-value is greater than the level of significance, we fail to reject the null hypothesis. In our case, the level of significance is 0.05, which we stated way back at the beginning of our problem. And the 0.1623 p-value is greater than the 0.05 level of significance. The p-value is greater than the level of significance, so we fail to reject the null hypothesis. Our conclusion is that, at the 5% level of significance, there is not enough evidence to suggest that the population mean quiz completion time of at least one of these sections differs from the others. Alright, my friends, that finishes our discussion of the OneWay ANOVA procedure. We will be exploring many more fun and exciting statistical topics that you won't want to miss, so make sure to check out our other videos.